Yeah, as you can see in my hand, it's a smoke detector. And yeah, I had a lot of free time in the weekend, and yesterday my landlord handed this over because there was some yeah, it needs to be reassessed and to test if it works, and the battery has to be replaced. So my landlord gave back to us, and then yeah, I had a lot of free time, so I was looking into how actually it works, because I never looked into it, and I think it was quite a fascinating journey of a lot of things that I explored. So this particular smoke detector works on certain principle. It's written over here, photoelectronische Rauchmelder. It is based on the photoelectronic effect, or in English we can say photoelectric, but I think photoelectronic is more accurate because we deal with small currents and also with a lot of electronic devices in here. So yeah, so actually I was like trying to understand this. So like this device itself, if you look, it's based on Tyndall effect. So basically there is a chamber, a smoke chamber, where the smoke reaches, and it's basically scatters the light that is projected in that chamber, and that scattering effect itself is called Tyndall effect. I mean, the way the light interacts with particle, and that was like the basic question that I was exploring after knowing how it works, but I won't go deeper into that right now. I'll explain what exactly is happening in this device. So basically there is a theory called Tyndall effect, and this theory is very well observed under certain assumptions, and that theory under certain assumptions, and we try to mimic those assumptions as close to the reality. And when we do a control experiment, we basically observe that effect best, and then it leads us to certain device that serve our purpose here to detect the smoke based on the scattering of the light when it is obstructed by particles of the smoke. So this is how it is, and basically we have like a source of light. It's a photonic source. Basically this source is, if you look at it, it's basically a device that emits electromagnetic waves in the visible spectrum, which is a light emitting diode. Before going deeper into diodes and stuff, I would like to a basic understanding of a diode or stuff like this, from like how can we generate a basic understanding of these things. So I will also explore that. And then what happens is that when the light is projected into this controlled chamber where the smokes collect, it basically has a lot of photodetectors, basically light detectors. And when there is a smoke in here in the chamber, it basically scatters all around this light, and the intensity of the light is measured in the form of current, or when it is detected by these detectors. There are like two ways which can detect. Like there's a light source that is hitting constantly a detector, so there is no change in the intensity, there is no change. And once it is obstructed, there is a change in there that can also tell us about the presence of smoke in the chamber. Or we can have like multiple smoke detectors, photodetectors here, which can tell us about that, which can basically ring an alarm after a certain intensity. The basic, when we do a controlled experiment, we have to basically, for the calibrations and certainty, like if we define it in terms of the noise, like if there is a constant, if there is a noise, for example, in terms of you say the light, there's like a light, or um, yeah, like for example, if it is exposed to a varying condition, like for example, if this chamber is exposed to the daylight or something which is varying, so you cannot achieve a certain calibration sensitivity, certainty with these photodetectors. And also, yeah, like it is a black box, and basically what it means is that there is no reflection of light, because what will happen if there is a reflection of light, you can have yeah, the photons can basically um, jump around and creates a distortion, and maybe a same photon can detect multiple times by the same detectors, and you will lose the essence of the purpose of the device. So that's why it has to be black box. Why black box? Like black itself means the absence of color. Like in terms of, if we look at the visible spectrum, and if we switch off that spectrum, you don't see anything. You don't, because of all visible surrounding is basically. So if we have a visible electromagnetic wave, and we don't want that we don't want that to reflect or bounce around, we basically try to mitigate or to reduce this effect in this chamber itself. Yeah, one very basic example you can do is that when you close your eyes, basically you're cutting off all the visible spectrum in your eyes, so you see nothing. I mean, there is, and that nothing you see is basically telling you about what visible spectrum is not. I mean, it takes some certain times to respond to that absence of color in your eyes, because yeah, your eyes adjust to it. So you see a little bit patches around in your eyes, but you see what it does, why it has to be a black box. Yeah, so my question was more related to, now we study about, okay, let's talk about these different, yeah, so my question was more about the source and what is this and how it works, because there are a lot of nature of the light itself that is interplaying, and there's a lot of concepts here. So when you see that a light behaves both as particle and as waves, and you cannot say with certainty one simultaneously for both the nature at one time. So basically, when the light interacts with the smoke particles, it displays its particle nature governed by wave. So basically, it's a particle governed by a wave nature. So the wavelength of the light itself is somehow linked to the particle size, and that effect is different based on the particle size, how the light interacts with those particles. And if you go like this is something that is not causing any change in the particle itself of the smoke, the light itself, it's just scattering around without any change in its characteristic. For example, if we look from the particle nature, the energy packets, like the photon itself, is characterized by its frequency or the wavelength, and there's no such changes happening when these particles are interacting. So that is one thing. But let's expand this idea. So for example, like according to when we expand this idea, there is a photon that is interacting on an atomic level with the electrons. How does electron interacts with a photon as a particle? And basically the electrons around a nucleus is so if you go to very atomic level, the particles are not very certain with their it exhibits more of its dual nature of wave and particle. So basically, it's you cannot be very certain about. Yeah, you cannot treat that as a very certain case of classical mechanics where you are certain about the positions of. So you deal in terms of probability distribution of the presence of electrons around an atom based on the energy it has. So the nucleus itself is trying to bring that electron in through the Coulomb forces, but the kinetic energy and the state itself of the electron is trying to maintain that energy level so that it remains in that region with a certain possibility or certain probability around that space. So when electron interacts with when the photon interacts with the electron, there's so many things that can happen. The energy packet, when we talk in terms of the particle nature of light, the energy packet itself depends on the frequency of the light itself. And this is also a very classical example of showing the quantized nature of electrons and light electromagnetic waves. So when the photon itself interacts with the electron, it can do a lot of things. It can basically, the energy could be absorbed by the electron to reach to a high state level, the high energy state, and this high energy state could it could be still within the atom but on a higher energy state, or it can leave the atom altogether. The electron can escape. So this is one phenomena that could happen. The other could happen is that the photon itself can impart part of its energy and the thing is that when it reaches to a higher energy state, and the rest of the energy is not sufficient to bring it to a higher state, like the quantization of the energy. So it basically ejects or rejects out the rest of the electromagnetic wave that the photon particle in a lower energy state with the lower frequency or higher wavelength, and you see a shift in the light itself. Sometimes you have an experiment where you expose, like for example, sodium with like these experiments are shown, but it shows the same effect. Like a sodium exposed to a yellow light, it glows, and after certain times it emits the yellow light itself. So basically it's trying to basically the light itself is now leaving the atoms itself, and the electrons is now going back to the lower energy state, and that light is emitted back. You see these effects, and one effect is that there could be a lot of, like, it could be a elastic scattering or inelastic scattering. The elastic means that it doesn't do any change and it reflects back, or so this interaction of photon with an electron can happen in an atom. And when we talk about how an electromagnetic wave is generated out of a device, so this is a wild thought about how photons. Now if we can do a controlled experiment, then we can emit electromagnetic waves in such a way. And one such thing would be to, like, for example, let's suppose in a clever way we have two elements that are fused together. Like this, I'm telling about the diode itself, the light emitting diodes, how they're made. And we have like these two are complementing each other in such a way that this has an excess of electron, this is a deficiency of electrons. And basically what happens is that when you provide, it's like you provide a certain excitation energy to the electrons to jump from here to there, and basically this is a lower energy state of electron and this is higher. So there is an energy gap between these two fused substances, you can say, for now. So when you provide certain excitation, the electrons jumps from a higher to a lower state, and basically when it jumps, this shift in the energy has to be, I mean, you have to balance the energy conservation. The shift is emitted out as electromagnetic waves, and this is governed by the energy gap. So you have like when you have a higher energy gap, you may have if you see in the frequency scale, you have a higher frequency electromagnetic waves, so it's pointing more to the blue region of the diode, of the electromagnetic spectrum. So this is how a light emitting diode, I mean, essentially works. And like you have a monochromatic light because it is only emitting only one range of one frequency. I mean, I'm not going to tell about how we can improve this. There are also a lot of things that I can talk about how we can improve, because the nature of the smoke itself is not same for all kind of hazard that could happen with smoke. So we have like a lot of different light sources with different wavelengths that can interact with differently with different nature of the smoke, and we have more sophisticated smoke detectors. So this one thing, and then what comes, the photodetector is like the opposite side, where we see when the light interacts with the electron, it can basically excite it and produces a current stream that you can measure. So this is the other spectrum. So I'm not really going to talk really deep. I'm just giving you an idea or a hint of how to start thinking about to have a basic understanding. I'm not going to talk about how this N and P works. Like there's a deficiency, which is, we call it a hole, and there's an excess, which we term as there's an excess of electron, there's a deficiency, and there's an energy gap between these two fused atoms together. So this is how it works, and there is one there's like a lot of things that you can talk about. Like I was talking about the probability distribution of, like, it's a wave function, or the electron itself cannot be localized, that it's here or there. It's like there is a certain probability around the atom where it's found most in that energy state, depending on the configuration of the nucleus itself. And so that is how electron behaves around a nucleus. And based on, like, I'm talking about this scattering a lot, and this scattering, I mean, when you see, there's like so much of literature around that, a lot of theory developed, like a relay type scattering, or like a shift. You see a red shift in the scattering, or a Tyndall effect itself, but it's more with bigger particles. This is more or less with the smaller particles in the range of in the comparable range of the wavelength. But it's more, I think here Tyndall effect is more appropriate here, how the scattering happens. And you see that with a higher frequency, with the lower wavelength, yeah, the scattering is more, and you see that effect also. For example, here, if there's the sun and then there's our Earth and it's rotating around and around a tilted axis and also revolving around the sun, you see that when you look on the middle side of the Earth, when it's the sunrise over here, you see the scattering phenomena when we have sunrise and a sunset on the opposite side. So it's like entering into the blue region and is exiting the blue region. So because the blue light scatters in these with when interacts with the particles of the cloud. And yeah, I was thinking about like it takes 24